Hello and welcome to our fourth lecture on the basics of hemodynamics. With these set of lectures here, we're going to look into the Pisa formula, the proximal isovelocity area, and its application for regurgitant lesions. And then we'll also address a simplified form of the Pisa formula, and then we'll address the limitations that are associated with the Pisa method. The Pisa method is another way when we use ultrasound to evaluate a regurgitant valve. It is also based on the same principle of the conservation of mass. It is also important to note that many students misinterpret isovelocity as isovolemic from previous physiological learning. This calculation makes the assumption that flow through the regurgitant orifice is equal to flow within the hemispheric shape of flow convergence. A radius is measured from the valve leaflets, and we obtain 2 pi r squared. Modifying our flow calculations that we know that flow is equal to cross-section area times the velocity, we can substitute in that flow is equal to 2 pi r squared times the velocity of the regurgitant lesion. But why do we use a velocity, a maximum velocity, and not a VTI? We're using a specific velocity defined on the machine to determine the radius and thus the hemisphere that we measure. The velocity at this point is neither accelerating or decelerating. It is uniform or unchanged, thus the term isovelocity. However, blood is accelerating as it moves closer to the orifice. Therefore, higher velocity equates to smaller radiuses. As blood progresses towards a regurgitant orifice, it increases in velocity and the hemispheres associated with each velocity progressively decrease in size. The specific velocity at any specific hemisphere is uniform. Expanding the equation of what goes in must come out, we see that flow through the regurgitant valve is equal to flow within the hemisphere. Expanding out, cross-section area times the velocity, cross-sectional times the velocity, and then substituting across with a little bit of algebra, the cross-sectional area of the regurgitant valve is equal to cross-sectional area of the hemisphere times the velocity of the hemisphere divided by the velocity of the regurgitant valve. Basically, we can substitute cross-section area to be the effective regurgitant orifice area, EROA, and then expanding upon further, we see 2 pi r squared times the velocity at aliasing, which is the hemisphere, aliasing divided by the velocity of the regurgitant lesion. The radius of a hemisphere is difficult to determine under normal imaging settings. To ensure the best representation of the color baseline is moved in the direction of the flow. Example, in most instances, this is downwards for mitral regurgitation and upwards in mitral stenosis. Putting Pisa into practice, with our example that we have here, if we had a MR velocity of 5.5 meters per second and a radius that we've actually measured here of 0.9 centimeters, and the radius velocity is here set with our aliasing velocity of 0.32 meters per second, we can pop it onto our calculation of 2 times 3.14 times 0.9 squared times 32. So substituting meters into centimeters, so 32 divided by 550. So our effective regurgitant orifice area is 0.3 centimeters squared or 30 millimeters squared. Regurgitant volumes can be calculated in the same manner as we've described previously. Regurgitant volume is equal to the effective regurgitant orifice area times the velocity time integral of the regurgitant valve. Note here we've moved back to VTI. We're assessing all the velocities moving through the valve over a period of time rather than at an instantaneous point. Using the values from the previous calculation, if we have a VTI of 230 centimeters, simply pop it in. Regurgitant volume is equal to 0.3 times 230, and we get a regurgitant volume of 68 mils. The Pisa method is readily utilized for the estimation of regurgitant volume severity. In the case of stroke volume calculation for mitral valve regurgitation, typically the LVOT is placed for sampling the normal stroke volume. But this can't be used when there is existing aortic regurgitation. Fortunately, the standard PISA calculation can be simplified. Not only is this a time-saving process, but is also useful for instances where the regurgitant jet is eccentric. Imaging is suboptimal or the sonographer is unable to obtain the jet alignment. We obtain the simplified PISA by setting machine-specific settings and making an assumption of the mitral regurgitation velocity. In a patient that is normotensive, we expect to see a pressure gradient between the LA and the LV of 100 millimeters of mercury. That is a velocity of 5 meters per second for the mitral regurgitant jet. We mustn't forget to convert meters per second to centimeters per second, and this becomes 500. We set the machine setting for aliasing velocity to be 0.4 meters per second, which is Vn in our equation here. We know that pi approximates 3.14, and thus working with our calculation that flow in the regurgitant valve is equal to flow in the hemisphere. Working with our PISA equation, we can substitute in the numbers. So 2 times 3.14 times the radius squared times 40 divided by 500. This then works out to be 251.2 times the radius squared divided by 500, or roughly the radius squared divided by 2. And here we have some reference ranges for our PISA calculation. So we can use the regurgitant orifice area and the actual radius that we measure to our first line of aliasing, and both will indicate whether we have mild, moderate, moderately severe, or severe regurgitation. As with the limitations seen with other stroke volume calculations, the radius is an important component, and error in the determination of the value will lead to an inaccurate valve regurgitant area orifice, such as a radius of 0.6 centimeters measured instead of 0.8 leads to an effective regurgitant orifice area of 18 millimeters squared instead of 32 millimeters squared. The radius is measured at specific points in time, such as early diastolic filling for the mitral valve or early diastolic for aortic regurgitation. An effective orifice estimate is made with the flow at that point in time. This will over or underestimate the true anatomical orifice area. Beat-to-beat variation, as seen in previous calculations, can lead to error. Thus, it is important that numerous measurements are taken. Even in sinus rhythm, a sonographer who averages 3 to 5 measurements will deliver a much more desirable result. In the presence of atrial fibrillation, bigeminy, or frequent ectopic beats, then 8 measurements will deliver an improved accuracy. There are also considerations for the determination of hemispheres. The isovelocity contours or effective shells flatten immediately proximal to the orifice, effectively changing the shape, and assume volume within this will be then incorrect. Using a baseline shift that's not too extreme, i.e. a higher velocity for the aliasing point, minimizes this effect. Additionally, the orifice shape may be irregular, so that a hemisphere doesn't accurately represent the shape of flow convergence. Another example with mitral regurgitation, where significant flow may arise from multiple points. In some instances, the regurgitation is eccentric, and the velocity cannot be accurately determined. And in this instance, the simplified PISA may be considered. The user may also be wary of other flows that may influence the hemisphere shape. High velocities through the LVOT, which may be seen in systolic flow obstruction or vigorous systolic function. The LVOT flow may contaminate the MR flow convergence and lead to the formation of a distorted hemisphere. The sonographer must also consider that structures do not remain stable in the imaging plane throughout the cardiac cycle. This is of particular importance to the atrioventricular valves in systole. In systole, the ventricle contracts not only circumferentially but also longitudinally. As a result, the atrioventricular valves descend towards the apex in systole, and this motion will add to the isovelocity of the hemisphere, making it effectively larger, and thus the user will overestimate the regurgitation severity. The effect of this is minimized when the appropriate baseline shift is used, so again, setting a higher aliasing velocity. Mitral valve prolapse can demonstrate an opposite effect to this. The mitral valves move towards the atria in systole, and this motion can lead to a subtraction in the isovelocity contours and an effective underestimation of the regurgitation severity. Prolapse further compounds the difficulty in estimation of severity, and that the phase of systole has significant impact on the result. The effective regurgitant orifice area and regurgitant volume vary in such a way that it's been established the most appropriate timing is to mid or later systole. Indeed, you may even note when obtaining MR velocities with prolapse that only the second half of a Doppler profile is observed. As we can see in this example here, mitral regurgitation actually starts here with the barrel click, but only with prolapse do we actually get the significant mitral regurgitation flow profile. So in the summary here, with the lecture we have explored the PISA method that uses the principle of contracting shells or hemispheres to estimate a volume of blood that therefore must pass through a regurgitant orifice. The conservation of mass principle therefore governs the PISA method. There is a simplified PISA application that can be used for competent valves not required. There are, however, a number of limitations and considerations that we need to be aware of, which include errors in measurements, machine settings, and potential distortion of hemispheres. All these need to be considered when and if ESA should be applied in the clinical setting.